Boom. Hello and welcome back to Calculus 3. Tonight on the menu, 12.8 minimum and maximum problems, which is where we find minimum and maximum on the shape. Now, we are first going to briefly take a look at Calc 1 and remember the procedure, and then just upgrade and modify it for Calc 3. So in Calculus 1, you know that you had a function of some sort, and that function had horizontal tangent line at every minimum, at every maximum, and the horizontal tangent line had the slope m equal to 0. Now we also know that the first derivative computed at 8 gives you that slope, and since it's equal to 0, that means that if you have a function of some sort, and then you take its derivative by setting it equal to 0, this x is the location of min-max. So you have some kind of the equation. Let's say you have y equals 3x minus 1 squared. Let's say this is your equation. And you wanted to find a min or a max, whatever this thing has. Well, it's clear what it has. It's a quadratic, but let's say we don't know. You would take the derivative as 6x minus 1. And then we would set this equal to 0. And you would come up with x equals to 1. And then you would take x equals to 1, plug that in the original equation, and get that y at 1 is 0, meaning that at 1, 0, we either had min or a max. And then you would do the first derivative test or the second derivative test, or you would, I don't know, look at, I don't know, throw the bones in something, or just look at the palm and know. But you will find whether it's a min or a max. Now, since this is a parabola that opens up, definitely it's a min, right? Because it's, 3 is positive, right? A is positive. So we know what it is, but you would generally do first or second derivative test to figure it out. So now, moving to Calculus 3, you know that your z is function of x and a y, and your input point is going to be a, b for the domain, and that will produce some kind of a z as the height. So now we start by, well, first of all, obviously definition for the min and the max is the highest point and the min is the lowest point. You all know those from Calc 1. We don't have to redefine all of that stuff. I just want to make sure that you understand that for this problem, the theorem states that if f of xy has a local minimum or maximum, value at a, b, that's the domain, and the partial derivatives fx and fy exist at AB, then fx computed at AB is the same as fy computed at AB. Those are the partial derivatives, and that's equal to 0. So in Calculus 1, you remembered set the derivative equal to 0 and solve the equation. Now set both partial derivatives, one at a time, equal to 0, and solve the equation. That will give us locations for min and max. Then you go and you figure out what they are. But remember that there was an issue here. We actually had not just min and max, but we also had that weird type of a point that we called a saddle point. Remember that one? The one that had two parabolas meet at the same point, and depending from which end you look at it, it's either a min or a max. Nope, saddle point for Calc 3. Yeah. So we'll have to have a method with which we are going to determine whether it's min or a max or the saddle point, and we are going to use the second derivative, and this is where the mixed partial derivatives come to play. So we'll have that as well. So this next theorem states that an interior point AB in the domain of f x y is called the critical point if either 1 fx at AB equals fy AB equals 0, or 2, at least one of the partial derivatives does not exist. I will just remind you from your Calculus 1 that absolute value of x function has a minimum and at 0, 0, and the derivative doesn't exist at that point. So that's one of the cases where second line helps. So now you're going to have a shape of a cone, right? A cone, ice cream cone, will have at the bottom minimum point, right? Because it goes into a point, and there's no derivative at that point, because either way you look at the partial derivatives, it ends in a spike, and they have two competing slopes at the same point, so there's no derivative at the spike of the cone. So that would be the place where the second one applies. Yeah, I'll draw a little cone here to remind you of that. 90% of the 99.7% of the time we are dealing with number one because we are computing stuff. But then, you know, eventually you might deal with something in engineering and you need to know these things. So there you have it. So how do you find the critical point? Simply set everything set the first partial derivatives equal to 0. I'm just going to get all the theory out of the way first, and then we are going to solve problems. So now we know that min and max will exist in a problem in the shape when the first and second derivatives are set to 0. We also have the critical point, which is where they occur, and those also can be found if the derivative does not exist. And now we're getting to a second derivative test, which is the one that we are going to use to discriminate between three different types of points that we have. So this is the big one. You will have to memorize this formula in order to solve problems. So the formula for the second derivative, this d of xy, is equal to the partial derivative xx times the second partial derivative xy, sorry, yy, and then minus the mixed partial derivative squared. So that is the formula that you have to memorize. Is just second partial in x times second partial of y minus the mixed partials squared. And the theorem says this. If d computed at AB is larger than 0, and the second partial derivative of x, so fxx, computed at AB is less than 0, we have a max. If DAB is larger than 0, and the first partial derivative at AB is also larger than 0, we have a min. 3. If this thing is less than 0, that's it. We have a saddle. And the last case, if DAB is equal to 0, test is inconclusive. Now, I will just remind you that you can, by brute force, figure out what it is, because if you have a shape that, let's say, has a max, if you move and that shape that has a max is over some point AB in your domain. If you move a little bit away from that AB, so let's say you are computing at 1, 2, that's your AB. If you go 0.9 and 2, you are already a little bit off from the point where your critical point is. You can actually figure out whether it's a min or a max, but if they all, so you go around, compute like 4 or 5 points around, and if they're all less than, in a z value, then what you had was a max. If they're all more than, then what you had is a min. And if some are less and some are more, well, it should be a saddle, right? So it's not all lost if this doesn't work, but it saves heck of a lot of time. So you want to use this all the time, obviously. And the second derivative is what you are memorizing. So we are done with the theoretical part here. You all understand min and max, and you all understand how this works from Calc 1. Now we just need to grind through a few examples, and then I'll see a little bit spicier examples later. Now, the examples that are done in the textbook, you can just read that stuff. You know all the letters, numbers, I hope. I would like to just get the random whatever problem. 19 through 28. Which one? 27. 27. Oh, you know how to pick. Yeah, we have this problem which Alex picked as the first problem. So good. Nothing to worry about. It's just 2xy e to the negative x squared y squared. It's not a problem. Alex chose it. He likes it.
What's the problem?
Analyze critical points, min and max. So I will tell you what to do, and then I will eventually do it. Find first partial derivative in x and y, set each one to 0, and solve them. So find both partial derivatives, set them equal to 0, and solve. All right, what do you have?
I just get very anxious around ridiculous. What's up? No. I don't remember why. No. Yeah, no, surprising. No, I was just hanging around last night. I didn't want to. It's such a far drive, and it's 25. No, it's 25 minutes from here. It's like a 40-minute drive from what? Ask Rich. 30-minute drive. Or drive. Which drive? Plus my Brad was already out anyways, and he's pretty much my drive for these things. Should have rode my bike. No. The other thing was, I was just really doing some serious housework. Kind of. Let me go check login times. Stop.
See if you logged in. We're going to do it on this public over here. See what time you logged in last time. Homework. All right, let's take a look at the partial derivatives. Oh, it's fine. So we have two partial derivatives to take. Fx first. So this is the derivative in respect to x-axis. And it's a product rule. So we have to deal with that. So copy the first times derivative of the second plus copy the second times derivative of the first. And now, when you factor out what you can, which is 2y e to the negative x squared minus y squared, what's left is negative 2x squared plus 1, I hope, right? And then we set this equal to 0, and we solve this equation. So we have three different factors here to worry about. Each one of these will be set to 0. I have 2y equal to 0 from where y is 0. I have e to the minus x squared minus y squared equal to 0, which has no solution, right, because it's exponential. It doesn't cut through x-axis. And then we have negative 2x squared plus 1 equal to 0, from where I have 2x squared equals to 1, from where x squared is equal to a half, x squared equals to a half, from where x is equal to plus minus root 2 over 2. So from this calculation, we find, sponsored by Alex, two critical points, root 2 over 2 comma 0 and negative root 2 over 2 comma 0. So we are halfway through, because that was all for the fx. Remember, guys, today's is all about having these obnoxiously long, tedious problems that are extremely easy. You find the first derivative, you set it equal to 0. So you did this in Calc 1 5,000 times, except here it's just long procedure. So now we repeat the entire screen you see here. Control-C, Control-V, replace x's with y's, right? So your answer now must be x's and y's replaced, which is going to be 0, comma root 2 over 2 and 0, comma negative root 2 over 2. But let's, and the only reason why is that so is because we started with a symmetric equation. But you know what? It's fun to compute these things. So fy it is. So copy the first one, 2xy, take the derivative of the second one, which is negative x minus x squared minus y squared times negative 2y, plus copy the second one, e to the minus x squared minus y squared times the derivative of the first, which is 2x. There we go. Now we are going to take out 2x e to the minus x squared minus y squared, which leaves behind negative 2y squared plus 1, and we set that equal to 0. Again, we have 3 parts to worry about. Just a little bit of algebra, nothing scary. We have 2x equal to 0 from where x is equal to 0. We have e to the minus x squared minus y squared equal to 0, which has no solution again. And then we have negative 2y squared plus 1 equal to 0, from where 2y squared is equal to 1, from where y squared is equal to 1/2, and then finally y equals to plus minus root 2 over 2, giving us 0 root 2 over 2 and 0 negative root 2 over 2. Those are also critical points. As I promised. So finally, half of the problem is done. This was us figuring out the critical points, right? The next is to figure out what these are. Min, max, or saddle. That means second partial derivative. Look at your first partial derivative. Isn't this fun? I told you, it's just tedious. I mean, nothing you can't take care of. It's just grind. So now let's see what they are. Yeah, we got time. We're here to midnight anyway. Are we? So now fxx. We have to find our first partial derivative. There it is. Fx. And take derivative of that. You know what? Because it's so nice, I'm going to actually first write this derivative so I can actually take the derivative underneath. So here we go. It was 2y e to the minus x squared minus y squared times negative 2x squared plus 1 equal to 0. And don't need equal to 0. Just need the derivative. So now fxx. It's a product rule. If you see that this function has x and this function has x, so it's not as scary as it looks. All the y's are constants. So you're taking the derivative in respect to x, you're copying, so 2y e to the minus x squared minus y squared, and then times the derivative of the, so copy the first, times the derivative of the second. The derivative of the second is just negative 4x. Right? Right. And then plus copy the second, there we go, times the derivative of the first. Well, you copy the constant and e, and then times the derivative of the exponent, which is negative 2x. Great. And now to simplify, right? If you carefully observe, we can factor out negative 2x. No, we can negative 4x. So fxx is negative 4x e to the negative x squared minus y squared. And then what's left? From the first term, this is out, this is out, so 2y. From the second term, the entire parenthesis, and then a y. Because this 2 and this negative 2 make a negative 4x. So, and then this is out as well. No! When you start doing this, that means it's gonna crash soon. Okay. So now we can simplify in the parenthesis. So you see that this plus y would create over here 3y. And we can kick that y outside. There we go. So if this is your fxx, then fyy, because it was symmetric, so we don't waste time, has to look the same. Except this is going to be like this. Awesome. Is the lab due today?
Yeah.
Is it done? No? All right. The only other part that it's left for us to compute is the mixed partial derivative fxy, because that one needs to be squared. It's not gonna be a problem. You have fx, just take the derivative in respect to y. So we are going to pair it differently. You have 2y here, and then the rest also has 1y. So copy the first one, times derivative of the second, which is e minus x squared minus y squared times negative 2y, and then times negative 2x squared plus 1. That was the first, plus. Copy the second, and then times 2. Easy. All right, now we simplify this one. What can we kick out? We can kick out this, and the 2. So I can kick out the entire term over there. 2 times negative 2x squared plus 1 times e to the negative x squared minus y squared. And what's left in the parenthesis is negative 4y squared plus 1. Done. I can box those that are important, because now, if you remember the formula said that d at AB is fxx times fyy minus fxy squared. Now you could write this all out and work it out, but you can also plug in values into equations there and check out. So I'm just going to do 1 of the 4, and obviously when you're doing homework you'll do all 4 because it's unlimited time, right? Oh, did I mention that each one of these problems is like 45 minutes? So let's find d at whatever the first one was 3 hours ago. Root 2 over 2, 0. All right, so pay attention. Y 0, that kills a lot of stuff. When y 0, everything dies. Everything dies. So that's a 0. Minus, when y is 0, what do I get here? I get 2, negative 2 times root 2 over 2 squared plus 1 times e to the negative root 2 over 2 squared minus 0. And then open the parenthesis times 1, so we don't need to compute that. Great. So this is all I have to compute. So that's further equal to negative 2. This is 2 over 4, 1/2, negative 1. This is 0. So the whole thing is equal to 0, and the test is inconclusive. Yay! Inconclusive on this point. Oh, yes. Oh. That means it's because it's symmetric, probably will be inconclusive on all other points. And unless there is some kind of algebraic mistake along the way, which would make it non-conclusive. Yes? Because this part over here is negative 1, and everything dies. High five. Yes?
Plug d root 2 over 2 comma 0 into fxx and fyy is got 0.
Because there is a y multiplying everything. If this y is 0 and multiplies everything else, it kills it. The one above has it as well.
So because one of those was 0, everything went 0. That's all.
Yep. And it looked like it's going to survive in the second one, but unfortunately over here it didn't. So negative 1 plus 1 is 0 times everything else again 0. So, but this problem again was one of the bottom ones. So of course it's going to be something off with it. Takes long time to compute all these derivatives and so on, but So test is inconclusive on this one if we calculated everything correct, which means that you would have to use some other witchcraft to figure out whether it's a min or a max. You can compute the points around, see, and so on. Let's pick something else. Do one more example. Anyone except Alex?
It's still the same.
19 through, well, now 26.
28.
I said 19 to 26.
Yeah, well, we did 27, and there's 16, 19 for 28, right?
Yeah. So you want 28. All right. Well, 28 is the next problem that has been.
Didn't you just say anyone but Alex? Then Alex said
No, he said it. No, Brandon said it. No, Brandon said it, so that's it. All right, Brandon. It's too late now. Here's the problem. X squared plus xy squared minus 2x plus 1. All right, guys, you know the drill. Take the partial derivatives, set them equal to 0 each one at a time, and go.
I said I would give him my PB&J. Where do you see the J on it? It's on the other side. It's red. It's red. Well, one blueberry, one grape was a J. I don't know, that's not even. Yeah, I was like, someone's like, yes, white on the road. They're like, are you not going to eat it? I'm going to eat it once I do this. Oh, yeah. 2x plus y Hey, Alex, I'm getting
Yeah.
You know what? I'm getting. I don't. Next time, break 8. Evan, how do I do this? Yes. Whatever you want to do. I said now I want to yeah, you just need to connect with it. But that's it.
All right, guys, let's take a look at this together. I'm doing the tech support over there. So first equation is this one. And then we have Fy, which would be 2xy equal to 0. The top equation can be solved by, well, the top equation is just a relationship between x's and y's. The second equation gives us x equals 0 and y equals 0 for 0, 0 point. But then we need to plug this 0 in a top equation as well. So the top equation tells us that y squared is equal to 2 minus 2x. And if x is equal to 0, we have y squared equal to 2, from where y is equal to plus minus root 2. So that gives us 0 root 2 and 0 negative root 2. And if y equals to 0, then you have 2 minus 2x equal to 0, from where 2x equals to 2 and x is equal to 1, which gives us 1, 0 point. So as you can see, we have 4 points to consider in this case. So let me go one more time through the whole procedure here. I found both partial derivatives and set both equal to 0. I recognized first that from the second equation I can get this, because when you set x equal to 0 and y equal to 0, well, that's already solved, which gives us 0, 0 point. Now, observe that in the first equation you cannot solve and get x equals a number or y equal a number, because it's equation that correlates x and y. But you already have that x can be 0 and y can be 0. So you are going to solve the first equation using first time x equal to 0, which gives us 2 points. And then if y is equal to 0, gives us additional point. So now we have 4 points to consider, but before we do that, we have to get the d, right, the second derivative test up and running. So fxx, it's just 2, and fyy is 2x. And fxy is 2y. So our dxy is 2 times 2x minus 2y squared, which gives me 4x minus 4y squared. And now I need to run all of the points against this. So I'll start at 0, 0. Well, I have 0 equals 0 inconclusive. So we use something else. We also have, was that 0 root 2? If I put 0 root 2, I have 0 minus, so negative 8. Observe that fxx is positive 2. So this is smaller than 0, and fxx is, oh, do we need anything larger than 0? What definition say? If it's less, it's what? Saddle, so we don't need this part. So that one is saddle. Then d0 negative root 2 is also negative 8, less than 0, so another saddle. And the last point, 1, 0, that one is going to be 4, that's larger than 0, and fxx larger than 0, so that one is min, right? Both. When I was Calc 3, I just remembered, hey, looking for a minimum, both larger than, right? Larger, it's a minimum. And because we use larger for the minimum, then the less than is the saddle. Whatever way you want. So that takes care of these types of problems. Your job is to find the partial derivatives, set them equal to 0, solve in any way you can these equations, and come up with. Now, inconclusive. Again, you compute points around and see if it's always on top. If it's not, then it could be saddle. So there are a few things that you can do. Okay. The last part of this lecture before we break is to look for the min and max on bound sets. So far, our shapes could extend to infinity, covering the infinite domain. But then you could have a shape that has edges. And the derivative would not account for the edge. So if I have a shape like this, right, which is, just put the rag on the finger, right, we see the max right there. And that one within the shape will be detected by your first partial, second partial derivative, and so on. But now, if you consider this shape, where on the edge, right, you have this local max. But look at this one over here on top. There's a max there. This highest max that you currently see on this rag will not be detected by your partial derivative, because this shape would probably continue to climb, and that would just be maybe midway going all the way up to whatever that max is. So this boundary min and max are not detected by your by the procedure so far. They are detected by Calc1 calculations. So this is what's happening now. Think of a stencil, all right, for cookie. And let's say that stencil is this, right? So if you are to take that stencil and cut into whatever shape you had, these edges where the stencil hit will leave parabolas and sine functions and whatever it is that this shape had once you cut it. And I will start bringing the Play-Doh. God damn. So, unless someone has Play-Doh? Of course, you're not three. Anyway, observe that this cut is done along parallel to x-axis, right? So if it's done parallel to x-axis, it's a YZ plane. So we can plug in a value where the line cuts through, and that would reduce your 3-variable problem into a 2-variable problem, and then you just unleash Calc1 upon it. You do 4 cuts, 4 Calc1 problems in addition to all of this, because this procedure takes care of all of the middle points, and the 4 Calc1 problems will take care of the boundary. The highest of all z values is the absolute max, the lowest of all z values. So let's say you find 4 points in the middle. And then you find an additional 2 points on the boundary. You have 6 points. 6 points, 6 z values. It's a bounded shape. That means that the highest of all z values has to be your absolute max. If you have 2 of those, then both are. The lowest of all minimum values, right, the lowest z that you get, the smallest value for z, is going to be the minimum. So let's take a look at one of those wonderful problems and see how that works. Say 56. fxy is x squared minus y squared. That's the shape. And the region R is bounded by cuts like this. Absolute x less than 1 and absolute y less than 1. Now, you need to be able to graph this region here to understand the cut, to understand the cookie cutter. Absolute value of x less than 1 means what? Right? And then the same thing for y. So what is my cookie cutter? What is this?
Oh, so that's just square.
That's just a square. That's just a square that cuts through the y equals 1, y equals -1, x -1, x +1. Boom. That's how you mathematically get the square down. Awesome. So let's take care of the inside first. fx is 2x equal to 0, x equals 0. Fy is -2y equal to 0, y equals 0. So the only point that I have on the inside of the shape is 0, 0. Now, to find fxx, fxx is going to be 2. fyy is going to be -2. And fxy is going to be 0. So D is 2 times -2 minus 0 squared, which is -4, which is always less than 0, which means what? Yes. You are remembering larger is minimum. Therefore, if you have a less than, it's a saddle. So we know there is a saddle point inside. Now we are going to take care of the boundary. So I have z equals f of xy equals x squared minus y squared. And I have x equals -1, x equals 1, y equals -1, y equals 1. So the first thing I do is I go for x is -1. When I plug in x is -1, equation becomes z equals -1 squared minus y squared, which is 1 minus y squared. I hope you see a parabola, right, that opens downwards. Do we see that? So I know how you are used to xy, but now the point of y, which is the height going up, is z, and x and y are inputs. So you're either going to have xz or yz, depending on which face you look at, right? So now I'm not going to draw, but if I could, I would. On this side, I would draw parabola like that, because the shape does that at the point where we cut with x equals -1 plane. So now you use calculus 1 to take care of this. But you can also, just because it's basic from calc 1, you can also know that there is a max, right? Because it opens downwards. And you know that max is, you already know x is -1. Y needs to be 1. Or y needs to be 0. No, y needs to be 0, right? Yeah, let's compute. I know it's a max. So 1 minus y squared is equal to 0. Y squared is equal to 0. No, equal to 1. So y equals plus minus 1. So as I plug in into equation up there, I have x is -1, y is positive -1, and z would be 0 in either of these cases. And they're all max. Z equals 1 squared minus y squared. It's again 1 minus y squared. Leads to the same points. All the calculations are the same.
Wait, is it -1 or 1 for your second?
Oh, yes, it's 1. Yep. Then we have z equals now y is -1. So that's going to be x squared minus -1 squared, which is equal to x squared minus 1. Now we see that's going to be a min. So x squared minus 1 equal to 0. X squared equals to 1. X equals plus minus 1. So the point is plus minus 1 comma -1 comma 0 when you plug everything in. And finally, z equals x squared minus 1 squared, which is again x squared minus 1, gives us plus minus 1, positive 1, and 0. And all of these are min values. Now, this is Calc 1. All of this, these 4 calculations were Calc 1. So now, all of these have zeros, either min or a max. And the saddle point at 0, 0 has 0. So, the hell? I really don't like it, but it is what it is. We can draw this in Mathematica, see how it looks like. Let's see if it. Last time I tried to use Mathematica on this with stream and everything else, did not have enough bandwidth, so the whole computer exploded. Let's see. Z equals x squared minus y squared?
Yeah.
Oh, perfect. It put it in a box we need. So let's see. Now I hope you see the downward opening parabola here. And the downward opening parabola on the other side. So those are the two that had 1 minus y squared. And then you have over here on the bottom, you have one that said x squared plus 1, or minus 1, sorry, x squared minus 1, and the one in the back as well. And you also see a 0, 0, 0 in the middle is the one where you have the saddle point. So you have a max and a max and a min, and then the saddle point in the middle. So that was the cookie cutter So I'm just happy that this actually worked very well. Now, when you install this, you'll be able to do these kind of things with the shape to really see how this looks like from, you know, multiple angles and so on, not just the angle that they give you. So install this if you haven't installed so far, and use it to get familiar with shapes. Great. All right, so that ends the first part, the first lecture. We are going to take a few minute break and then work on Lagrange 12.9.